This is Chapter 5, Book 1 of A Journey in Other Worlds. This LibriVox recording is in the public domain. Recording by Tom Weiss. A Journey in Other Worlds, Chapter 5. Dr. Cortland's History Continued. In marine transportation, we have two methods, one for freight and another for passengers. The old-fashioned, deeply immersed ship has not changed radically from the steam and sailing vessels of the last century, except that electricity has superseded all other motive powers. Steamers gradually pass through the 500, 600, and 700-foot long class, with other dimensions in proportion, till their length exceeded 1,000 feet. These were very fast ships, crossing the Atlantic in 4.5 days, and were almost as steady as houses in even the roughest weather. Ships at this period of their development had also passed through the twin and triple screw stage to the quadruple, all four together developing 140,000 indicated horsepower and being driven by steam. This, of course, involved sacrificing the best part of the ship to her engines, and a very heavy idle investment while in port. Storage batteries with plates composed of lead or iron, constantly increasing in size, had reached a fair state of development by the close of the 19th century. During the second decade of the 20th century, the engineers decided to try the plan of running half of a transatlantic liner's screws by electricity generated by the engines for driving the others while the ship was in port, this having been a success already on a smaller scale. For a time, this plan gave great satisfaction, since it diminished the amount of coal to be carried and the consequent change of displacement at sea, and enabled the ship to be worked with a smaller number of men. The batteries could also, of course, be distributed along the entire length, and placed where space was least valuable. The construction of such huge vessels called for much governmental river and harbor dredging, and a ship drawing 35 feet can now enter New York at any state of the tide. For ocean bars, the old system of taking the material out to sea and discharging it still survives, though a jet of water from force pumps directed against the obstruction is often employed with quick results. For river work we have discovered a better method. All the mud is run back, sometimes over a mile from the river bank, where it is used as a fertilizer by means of wire railways strung from poles. These wire cables combine in themselves the functions of trolley wire and steel rail, and carry the suspended cars, which empty themselves and return around the loop for another load. Often the removed material entirely fills small, saucer-shaped valleys or low places, in which case it cannot wash back. This improvement has ended the necessity of building jetties. The next improvement in sea traveling was the marine spider. As the name shows, this is built on the principle of an insect. It is well known that a body can be carried over the water much faster than through it. With this in mind, builders at first constructed light framework decks on large watertight wheels, or drums, having paddles on their circumferences to provide a hold on the water. These they caused to revolve by means of machinery on the deck, but soon found that the resistance offered to the barrel wheels themselves was too great. They therefore made them more like centipedes, with large bell-shaped feet, connected with a superstructural deck by ankle-jointed pipes, through which, when necessary, a pressure of air can be forced down upon the enclosed surface of the water. Ordinarily, however, they go at great speed without this, the weight of the water displaced by the bell feet being as great as that resting upon them. Thus they swing along like a pacing horse, except that there are 4 rows of feet instead of 2, each foot being taken out of the water as it is swung forward, the first and fourth, and second and third rows being worked together. Although, on account of their size, which covers several acres, they can go in any water, they give the best results on Mediterraneans and lakes that are free from ocean rollers, and, under favorable conditions, make better speed than the 19th century express trains, and of course, going straight as the crow flies, and without stopping, they reach a destination in considerably shorter time. Some passengers and express packages still cross the Atlantic on spiders, but most of these light cargoes go in a far pleasanter and more rapid way. The deep displacement vessels, for heavy freight, make a little better speed than was made by the same class 100 years ago, but they are also run entirely by electricity, largely supplied by wind and by the tide turning their motors, which become dynamos while at anchor in any stream. They therefore need no bulky boilers, engines, sails, or coal bunkers, and consequently can carry unprecedentedly large cargoes with comparatively small crews. The officers on the bridge, and the men in the crow's nest, the way to which is by a ladder inside the mast to protect the climber from the weather, are about all that is needed, while disablement is made practically impossible by having 4 screws, each with its own set of automatically lubricating motors. This change, like other labor-saving appliances, at first resulted in laying off a good many men, the least satisfactory being the first to go. But the increase in business was so great that the intelligent men were soon re-employed as officers at higher rates of pay and more interesting work than before, while they as consumers were benefited as much as anyone else by the decreased cost of production and transportation. With a view to facilitating interchange still further, our government has gradually completed the double coastline that nature gave us in part. This was done by connecting islands separated from shore by navigable water and leaving openings for ingress and exit but a few hundred yards wide. The breakwaters required to do this were built with cribbing of incorrodible metal, affixed to deeply driven metallic piles, and filled with stones along coasts where they were found in abundance or excess. This, while clearing many fields and improving them for cultivation, provided just the needed material, since irregular stones bind together firmly, and, while also insoluble, combine considerable bulk with weight. South of Hatteras, where stones are scarce, the sand dredged from parts of the channel was filled into the crib, the surface of which has a concave metallic cover, a trough of still water being often the best barrier against the passage of waves. This double coastline has been a great benefit, and propelled vessels of moderate draught can range in smooth water, carrying very full loads, from Labrador to the Orinoco. The exits are, of course, protected by a line of cribbing a few hundred feet to seaward. The rocks have been removed from all channels about New York and other commercial centers, while the shallow places have been dredged to a uniform depth. This diminishes the dangers of navigation, and considerably decreases the speed with which the tides rush through. Where the obstructions consisted of reefs surrounded by deep water, their removal with explosives was easy, the shattered fragments being allowed to sink to the bottom and remain there beneath the danger line. Many other great works have also been completed. The canals at Nicaragua have been in operation many years, it having been found best to have several sizes of locks, and to use the large ones only for the passage of large vessels. The improved Erie and Champlain canals also enable ships 400 feet long to reach New York from the Great Lakes via the Hudson River. For flying, we have an aeroplane that came in when we devised a suitable motor power. This is obtained from very light paper cell batteries that combine some qualities of the primary and secondary type, since they must first be charged from a dynamo, after which they can supply full currents for 100 hours, enough to take them around the globe, while partly consuming the elements in the cells. The power is applied through turbine screws, half of which are capable of propelling the flat deck in its inclined position at sufficient speed to prevent its falling. The moving parts have ball bearings and friction rollers, lubrication being secured automatically, when required, by a supply of Vaseline that melts if any part becomes hot. All the framing is of thin, but very durable, galvanized aluminum, which has superseded steel for every purpose in which weight is not an advantage, as in the permanent way on railways. The airships, whose length varies from 50 to 500 feet, have rudders for giving a vertical or a horizontal motion, and several strengthening keels that prevent leeway when turning. They are entirely on the principle of birds, maintaining themselves mechanically, and differing thus from the unwieldy balloon. Starting as if on a circular railway, against the wind, they rise to a considerable height, and then, shutting off the batteries, coast down the aerial slope at a rate that sometimes touches 500 miles an hour. When near the ground, the helmsman directs the prow upward, and, again turning on full current, rushes up the slope at a speed that far exceeds the eagle's, each drop of 2 miles serving to take the machine 20 or 30, though if the pilot does not wish to soar, or if there is a fair wind at a given height, he can remain in that stratum of the atmosphere by moving horizontally. He can also maintain his elevation when moving very slowly, and though the headway be entirely stopped, the descent is gradual on account of the aeroplane's great spread, the batteries and motors being secured to the underside of the deck. The motors are so light that they develop 2 horsepower for every pound of their weight, while to keep the frames thin, the necessary power is obtained by terrific speed of the moving parts, as though a steam engine, to avoid great pressure in its cylinders, had a long stroke and ran at great piston speed, which, however, is no disadvantage to the rotary motion of the electric motor, there being no reciprocating cranks, etc., that must be started and stopped at each revolution. To obviate the necessity of gearing to reduce the number of revolutions to those possible for a large screw, this member is made very small, and allowed to revolve 3,000 times a minute, so that the requisite power is obtained with great simplicity of mechanism, which further decreases friction. The shafts, and even the wires connecting the batteries with the motors, are made large and hollow, though the primary battery, pure and simple, as the result of great recent advances in chemistry, seems to be again coming up, the best aeroplane batteries are still of the combination storage type. These have been so perfected that 8 ounces of battery yield 1 horsepower for 6 hours, so that 2 pounds of battery will supply a horsepower for 24 hours, a small 50 horsepower aeroplane being therefore able to fly 4 days with a battery weight of but 400 pounds. Limestone and clarified acid are the principal parts of these batteries. It was known long ago that there was about as much imprisoned solar energy in limestone as in coal, but it was only recently that we discovered this way of releasing and using it. Common salt plays an important part in many of our chemical reactions. By combining it with limestone and treating this with acid jelly, we also get good results on raising to the boiling point. However enjoyable the manly sport of yachting is on water, how vastly more interesting and fascinating it is for a man to have a yacht in which he can fly to Europe in one day, and with which the exploration of tropical Africa or the regions about the poles is mere child's play, while giving him so magnificent a bird's eye view. Many seemingly insoluble problems are solved by the advent of these birds. Having as their halo the enforcement of peace, they have in truth taken us a long step towards heaven, and to the cooperation and higher civilization that followed we shall owe much of the success of the great experiment on Mother Earth now about to be tried. Another change that came in with a rush, upon the discovery of a battery with insignificant weight, compact form, and great capacity, was the substitution of electricity for animal power for the movement of all vehicles. This, of necessity, brought in good roads, the results obtainable on such being so much greater than on bad ones that a universal demand for them arose. This was, in a sense, cumulative, since the better the streets and roads became, the greater the inducement to have an electric carriage. The work of opening up the country far and near, by straightening and improving existing roads, and laying out new ones that combined the solidity of the Appian Way with the smoothness of modern asphalt, was largely done by convicts, working under the direction of state and government engineers. Every state contained a horde of these unprofitable boarders, who, as they formerly worked, interfered with honest labor, and when idle got into trouble. City streets had been paved by the municipality, country roads attended to by the farmers, usually very unscientifically. Here was a field in which convict labor would not compete, and an important work could be done. When once this was made the law, every year showed improvement, while the convicts had useful and healthful occupation. The electric phaetons, as those for high speed are called, have 3 and 4 wheels, and weigh, including battery and motor, 400 to 4,000 pounds. With hollow but immensely strong galvanically treated aluminum frames and pneumatic or cushioned tires, they run at 35 or 40 miles an hour on country roads, and attain a speed over 40 on city streets, and can attain this rate without recharging for several days. They can therefore roam over the roads of the entire hemisphere, from the fertile valley of the Peace and gray shores of the Hudson Bay, to beautiful Lake Nicaragua, the River Plate, and Patagonia, improving man by bringing him close to nature, while they combine the sensations of coasting with the interest of seeing the country well. To recharge the batteries, which can be done in almost every town and village, 2 copper pins, attached to insulated copper wires, are shoved into smooth bored holes. These drop out of themselves by fusing a small lead ribbon. Owing to the increased resistance, when the acid in the batteries begins to boil, though there is, of course, but little heat in this, the function of charging being merely to bring about the condition in which part of the limestone can be consumed, the batteries themselves, when in constant use, requiring to be renewed about once a month. A handle at the box seat turns on any part of the attainable current, for either going ahead or reversing, there being 6 or 8 degrees of speed for both directions, while the steering is done with a small wheel. Light but powerful batteries and motors have also been fitted on bicycles, which can act either as auxiliaries for hill climbing, or in case of headwind, or they can propel the machine altogether. Gradually, the width of the streets became insufficient for the traffic, although the elimination of horses and the consequent increase in speed greatly augmented their carrying capacity, until recently a new system came in. The whole width of the avenues and streets in the business parts of the city, including the former sidewalks, is given up to wheel traffic, an iron ridge extending along the exact center to compel vehicles to keep to the right. Strips of nickel, painted white, and showing a bright phosphorescence at night, are let into the metal pavement flush with the surface, and run parallel to this ridge at distances of 10 to 15 feet, dividing each half of the avenue into 4 or 5 sections, their width increasing as they approach the middle. All trucks or drays moving at less than 7 miles an hour are obliged to keep in the section nearest the building line. Those running between 7 and 15 in the next, 15 to 25 in the third, 25 to 35 in the fourth, and everything faster than that in the section next to the ridge, unless the avenue or street is wide enough for further subdivisions. If it is wide enough for only 4 or less, the fastest vehicles must keep next to the middle, and limit their speed to the rate allowed in that section, which is marked at every crossing in white letters, sufficiently large for him that runs to read. It is therefore only in the wide thoroughfares that very high speed can be obtained. In addition to the crank that corresponds to a throttle, there is a gauge on every vehicle, which shows its exact speed in miles per hour, by gearing operated by the revolutions of the wheels. The policemen on duty also have instantaneous kodaks mounted on tripods, which show the position of any carriage at half and quarter-second intervals, by which it is easy to ascertain the exact speed, should the officers be unable to judge it by the eye. So there is no danger of a vehicle's speed exceeding that allowed in the section in which it happens to be, neither can a slow one remain on the fast lines. Of course, to make such high speed for ordinary carriages possible, a perfect pavement has become a sine qua non. We have secured this by the half-inch sheet of steel spread over a carefully laid surface of asphalt, with but little bevel, and though this might be slippery for horses' feet, it never seriously affects our wheels. There being nothing harder than the rubber ties of comparatively light drays upon it, for the heavy traffic is carried by electric railways underground, it will practically never wear out. With the application of steel to the entire surface, car tracks become unnecessary, ordinary wheels answering as well as those with flanges, so that no new tracks were laid, and finally the car companies tore up the existing ones, selling them in many instances to the municipalities as old iron. Our streets also need but little cleaning, neither is the surface continually indented, as the old cobblestones and Belgian blocks were, by the pounding of horses' feet, so that the substitution of electricity for animal power has done much to solve the problem of attractive streets. Scarcely a ton of coal comes to Manhattan Island or its vicinity in a year. Very little of it leaves the mines, at the mouths of which it is converted into electricity and sent to the points of consumption by wire, where it is employed for all uses to which fuel was put, and many others. Consequently, there is no smoke, and the streets are not encumbered with coal carts, the entire width being given up to carriages, etc. The ground floors in the business parts are used for large warehouses, trucks running in to load and unload. Pedestrians therefore have sidewalks level with the second story, consisting of glass floors let into aluminum frames, while all street crossings are made on bridges. Private houses have a front door opening on the sidewalk, and another on the ground level, so that ladies paying visits or leaving cards can do so in carriages. In business streets, the second story is used for shops. In place of steel covering, country roads have a thick coating of cement and asphalt over a foundation of crushed stone, giving a capital surface, and have a width of 33 feet, 2 rods, in thinly settled districts, to 63 feet, or 4 rods, where the population is greater. All are planted with shade and fruit trees, while the wide driveways have one or two broad sidewalks. The same rule of making the slow-moving vehicles keep near the outside prevails, though the rate of increase in speed on approaching the middle is more rapid than in cities, and there is usually no dividing ridge. On reaching the top of a long and steep hill, if we do not wish to coast, we convert the motors into dynamos, while running at full speed, and so change the kinetic energy of the descent into potential in our batteries. This 20th century stage-coaching is one of the delights to which we are heirs, though horses are still used by those that prefer them. We have been much aided in our material progress by the facility with which we obtain the metals. It was observed some time ago that when artesian and oil wells had reached a considerable depth, what appeared to be drops of lead and antimony came up with the stream. It finally occurred to a well borer that if he could make his drill hard enough and get it down far enough, keeping it cool by solidified carbonic acid during the proceeding, he would reach a point at which most of the metals would be viscous, if not actually molten, and on being freed from the pressure of the crust they would expand, and reach the surface in a stream. This experiment he performed near the hot geysers in Yellowstone Park, and what was his delight, on reaching a depth scarcely half a mile beyond his usual stopping place, to be rewarded by a stream of metal that heralded its approach by a loud explosion and a great rush of superheated steam. It ran for a month, completely filling the bed of a small dried-up river, and when it did stop, there were 10,000,000 tons in sight. This proved the feasibility of the scheme, and though many subsequent attempts were less successful, we have learned by experience where it is best to drill, and can now obtain almost any metal we wish. Magnetic eyes are of great use to miners and civil engineers. These instruments are something like a mariner's compass, with the sensitiveness enormously increased by galvanic currents. The eye, as it were, sees what substances are underground, and at what distances. It also shows how many people are in an adjoining room, through the magnetic properties of the iron in their blood, whether they are moving, and in what directions and at what speed they go. In connection with the phonograph, and concealed by draperies, it is useful to detectives, who, through a registering attachment, can obtain a record of everything said and done. Our political system remains with but little change. Each state has still 2 United States senators, though the population represented by each representative has been greatly increased, so that the Senate has grown numerically much more than the House. It is the duty of each member of Congress to understand the conditions existing in every other member's state or district, and the country's interest always precedes that of party. We have a comprehensive examination system in the civil service, and every officeholder except members of the cabinet retains his office while efficiently performing his duty without regard to politics. The President can also be re-elected any number of times. The cabinet members, as formerly, usually remain in office while he does, and appear regularly in Congress to defend their measures. The really rapid transit lines in New York are underground, and have 6 tracks, 2 being used for freight. At all stations, the local tracks rise several feet towards the street and slope off in both directions, while the express tracks do this only at stations at which the faster trains stop. This gives the passengers a shorter distance to descend or rise in the elevators, and the ascent before the stations aids the brakes in stopping, while the drop helps the motors to start the trains quickly in getting away. Photography has also made great strides, and there is now no difficulty in reproducing exactly the colors of the object taken. Telephones have been so improved that one person can speak in his natural voice with another in any part of the globe, the wire that enables him to hear also showing him the face of the speaker, though he be at the antipodes. All telephone wires being underground and kept by themselves, they are not interfered with by any high-tension electric light or power wires, thunderstorms, or anything else. Rain-making is another subject removed from the uncertainties, and has become an absolute science. We produce clouds by explosions in the atmosphere's heights, and by surface air forced by blowers through large pipes up the side of a mountain or natural elevation, and there discharged through an opening in the top of a tower built on the highest part. The aeroduct is encased in a poor heat conductor, so that the air retains its warmth until discharged, when it is cooled by expansion and the surrounding cold air. Condensation takes place, and soon serves to start a rain. Yet, until the earth's axis is straightened, we must be more or less dependent on the eccentricities of the weather, with extremes of heat and cold, droughts and floods, which last are of course largely the result of several months' moisture held on the ground in the form of snow, the congestion being relieved suddenly by the warm spring rains. Medicine and surgery have kept pace with other improvements, inoculation and antiseptics, as already seen, rendering most of the germ diseases and formerly dreaded epidemics impotent, while through the potency of electrical affinity we form wholesome food products rapidly, instead of having to wait for their production by nature's slow processes. The metric system, now universal, superseded the old-fashioned arbitrary standards, so prolific of mistakes and confusion about a century ago. English, as we have seen, is already the language of 600 million people, and the number is constantly increasing through its adoption by the numerous races of India, where even before the close of the last century it was about as important as Latin during the greatness of Rome, and by the fact that the Spanish and Portuguese elements in Mexico and Central and South America show a constant tendency to die out, much as the population of Spain fell from 30 million to 17 million during the 19th century. As this goes on in the Western Hemisphere, the places left vacant are gradually filled by the more progressive Anglo-Saxons, so that it looks as if the study of ethnology in the future would be very simple. The people with cultivation and leisure, whose number is increasing relatively to the population at each generation, spend much more of their year in the country than formerly, where they have large and well cultivated country seats, parts of which are also preserved for game. This growing custom on the part of society, in addition to being of great advantage to the out-of-town districts, has done much to save the forests and preserve some forms of game that would otherwise, like the buffalo, have become extinct. In astronomy we have also made tremendous strides. The old-fashioned double convex lens used in telescopes became so heavy as its size grew that it bent perceptibly from its own weight when pointed at the zenith, distorting the vision, while when it was used upon a star near the horizon, though the glass on edge kept its shape, there was too much atmosphere between it and the observed object for successful study. Our recent telescopes have, therefore, concave plate-glass mirrors, 20 meters in diameter, like those used for converging the sun's rays in solar engines, but with curves more mathematically exact, which collect an immense amount of light and focus it on a sensitive plate, or on the eye of the observer, whose back is turned to the object he is studying. An electrical field also plays an important part, the electricity being as great an aid to light as in the telephone it is to sound. With these placed generally on high mountain peaks beyond the reach of clouds, we have enormously increased the number of visible stars, though there are still probably boundless regions that we cannot see. These telescopes have several hundred times the power of the largest lenses of the 19th century, and apparently bring Mars and Jupiter, when in opposition, within 1,000 and 10,000 miles respectively, so that we study their physical geography and topography, and we have good maps of Jupiter and even of Saturn, notwithstanding their distance and atmospheric envelopes, and we are able to see the disks of third magnitude stars. It seems as if, when we wish any particular discovery or invention, in whatever field, we had but to turn our efforts in its direction to obtain our desire. We seem, in fact, to have awakened in the scenes of the Arabian Nights. Yet the mysterious genius which we control, and which dims Aladdin's lamp, is the gift of no fairy godmother sustained by the haze of dreams, but shines as the child of science, with fadeless and growing splendor, and may yet bring us and our little planet much closer to God. We should indeed be happy, living as we do at this apex of attained civilization, with the boundless possibilities of the future unfolding before us, on the horizon of which we may fairly be said to stand. We are freed from the rattling granite pavement of only a century ago, which made the occupant of an omnibus feel like a fly inside of a drum, from the domination of our local politics by ignorant foreigners, and from country roads that either filled the eyes, lungs, or hair of the unfortunates traveling upon them with dust, or resembling plowed and fertilized fields, saturated and plastered them with mud. These miseries, together with seasickness in ocean traveling, are forever past, and we feel that Excelsior is indeed our motto. Our new and increasing sources of power have so stimulated production and manufacturing that poverty or want is scarcely known, while the development of the popular demand as a result of the supplied need is so great that there is no visible limit to the diversification of industry or the possibilities of the arts. It may seem strange to some that apparently so disproportionate a number of inventions have been made in the last century. There are several reasons. Since every discovery or advance in knowledge increases our chance of obtaining more, it becomes cumulative, and our progress is in geometric instead of arithmetical ratio. Public interest and general appreciation of the value of time have also effectively assisted progress. At the beginning of each year, the President, the governors of the states, and the mayors of cities publish a prospectus of the great improvements needed, contemplated, and under way within their jurisdiction. It may be planning a new boulevard, a new park, or an improved system of sewers, and at the year's end they issue a resume of everything completed, and the progress in everything else. And though there is usually a great difference between the results hoped for and those attained, the effect is good. The newspapers publish at length the recommendations of the executives, and also the results obtained, and keep up public interest in all important matters. Free to delve in the allurement and fascination of science, emancipated man goes on subduing nature, as his Maker said he should, and turning her giant forces to his service in his constant struggle to rise and become more like him who gave the commandments and showed him how he should go. Notwithstanding our strides in material progress, we are not entirely content. As the requirements of the animal become fully supplied, we feel a need for something else. Some say this is like a child that cries for the moon, but others believe it is the awakening and craving of our souls. The historian narrates but the signs of the times, and strives to efface himself, yet there is clearly a void, becoming yearly more apparent, which materialism cannot fill. Is it some new subtle force for which we sigh, or would we commune with spirits? There is, as far as we can see, no limit to our journey, and I will add, in closing, that, with the exception of religion, we have most to hope from science. This is the end of Chapter 5 in Book 1 of A Journey in Other Worlds. Recording by Tom Weiss.